You guys signed it and gave it to who? Or you gave it in front and they are saying they sent it back. Oh, sheet is here. Oh, it was. Everyone has his name here in the sheet? Yes? You both don't have it. So, well, you will be mentors for some of these teams. So, I think the project topic should come from you all rather than me assigning it. Okay, so decide on a project topic that interests you. For example, he's talking about latest affairs, current affairs topics, which is quite reasonable, right? As far as research, precise research objective is concerned, we all will help you in that. So it will not be random just. It will be a significant research objective questions that will be worth publishing it in a journal. Okay, so we'll continue with the mathematical analysis. So again, we are not going into very high level bifurcation analysis. We want to get a flavor of it. It's not a mathematics course. It's a course on data driven aspects, thinking process to change on the model. Okay, so this is the model that we have before, but yeah, it has some simulations also. But so basically, you have this is fitting. This is simple models and fitting a 1978 influenza epidemic in boarding school in England. Now, why did we use this outbreak? You know, it's very difficult to model, to get a data for the model. Why? Because if you are modeling, let's say, a whole nation, you know, there are people moving out of the nation, they are coming in of the nation also. So you have to model immigration and emigration also, which is very, very challenging. It becomes very challenging to get the data on that. So this is using boarding school data. What does the boarding school does? You cannot go out, right? It's restricted. So that's why this data is very good to get an understanding about the model. So basically, it uses, there were 763, it's a boys' school, boarding school, and 763 boys, and one of the boy came back from winter's break with the flu-like symptoms. And they wanted to see how many people will get infected, how many boys will get infected. So, and they basically ran similar. So initial condition was everyone susceptible except one person, right? And they calculated these assays. So how did they calculate it? Well, they ran a reference point from the literature, and they wanted to see which one. They choose different betas in these ranges. They choose different gammas, beta and gamma combination in these ranges. And for fixed value of beta and gamma, you can run one outbreak, right? So in order for this model to simulate, you need one value of beta, one value of gamma, and initial condition. That's it. So if you give one beta and one gamma, you will get one curve. Right? That was what we saw in the previous slide. So we used so MATLAB basically we described we had this data looks like this. So first day there was the person who came from outside, the one boy that was infected, but after one day there were 3 people infected, 3 boys were infected. After second day, 6 boys, and so on and so forth. So epidemic peaked around this 8th day. And within 15 days, the epidemic is over. So the way to in the MATLAB that we simulated, we estimate the model and we get the data, is first we have to describe the function for the system, the equations. Remember the model that we have, these equations. You have to write in the MATLAB. So this is the system, which is SIR is the system equation. So beta and gamma are parameters, and S, I, and R are the compartments. So these are the three equations: minus beta Si plus beta Si and minus gamma I plus gamma I. Beta Si, gamma I, and gamma I here. So those are the things are defined in this differential. This is differential equations. This is a differential equation, and this is a system. And then you have the data. The data is stored in for different days in an array form for different time points. 14 days. It took 14 days for initial condition. In fact, one came, and the first day there were 3 infected. So we take the first day as infection. 763 were the boys total, 3 infected, and remaining this thing. So this is the initial condition. Y0 is equal to 760 is the susceptible, infected is 3, and 0 is recovered. And then we simulate it. Simulating, we are using a function called OD45. How many of you have used MATLAB? Okay, let me ask a different question. How many of you have not used the MATLAB?
I have basic idea.
Yeah, basic idea you have, right? So almost all of you guys. So basically this function is important here. To run this function is calling this SIR function. See, this is the SIR function. This is being called by OD45. OD45 is an inbuilt function that is solving the SIR system. And then you plot the model. So basically, this is what is being done: data, model, and simulating of the model. Now, in order to simulate the model, where is the simulation happening? This is the simulating of R. You are computing for initial conditions and for the parameters P0. P0 is, where is P0? Sorry, P. P is beta and gamma. These are P basically. What are you saying? I didn't get you. Anyone saying something? So this is the initial value. Beta is this and gamma is that. That goes in an input for the parameters. Y0 is initial condition. T span is the time. Different time we are taking 1 to 14. And T final, this time is same as T span. That is T span. And SIR is the function. Here is the function. So this simulates for one fixed beta and one fixed gamma. This function simulates. And the next is the plotting. Okay, but this is done only for one value of beta and one value of gamma. Now what we want to do is estimate what is the right beta and what is the right gamma that gives me that data that we have obtained. Remember, the data looks like what? Data is this, right? This is coming from the hospitals in the boarding school. First day these many patients. Second day that many patients, so on and so forth, right? So now we are in, so once this model is working with the one fixed beta and gamma, that beta and gamma we don't know yet, right? It is just arbitrary value of beta and arbitrary value of gamma. This whole thing can simulate. But now we want to know exact beta and exact gamma that will actually capture the data set. I want the data set to be captured by that model. So that's where this function starts to come into picture, residual and optimization. So I'm using this as a new function now, which is basically finding, you see it is calculating residuals. I minus I data. I from the model and I data from the actual data. So this difference is the residual. Is that making sense? Yes, no? Do you know what is residuals? Right? So this is the residuals. Basically it shows the difference from, this is the data, and the model is, so for fixed value of beta and gamma, it is plotting one curve. It is plotting one curve. So it is looking at the residuals of those data points and the curve. What does that residuals look like, right? And that is what is computed here. And so this is a function that computes the residuals given one curve. One curve and the data gives you the residuals. Now what this another function which is called LSQ and non-lin is the inbuilt function in MATLAB which is optimizing. And basically what it does is it takes this function and run it for different beta in this range. It takes now it randomly sample one beta, randomly sample one gamma, and for that combination of beta and gamma I simulate one curve and find the residual. Then it takes one more beta and one more gamma, it plots one more curve and compute the residual, right? And then it finds the minimal residuals pair of beta and gamma, right? Does that make sense or no? There's no board here also. So anyway, so it's basically optimizing this thing, and it is finding which beta and gamma will give you the lowest residual, good fit to the curve. Is that what you guys have done before? Any one of you? Optimization of the. So basically, this is how we do it for the for finding the parameter, right? Parameter combination, because we want to know what is my beta and what is my gamma that will fit the data. That will fit the data. So that is what will spit out to me. I will share this codes with you, so you will have that one. But this is how we know exact beta and gamma. There's an assignment here where you have a data for a different disease, and there is some work that you can do it with that. But again, this slide is with you. You can always do. So this is the goal for most of the work. In most of the work, what we do is we build a model. We have to then find the right combinations of the parameters that will result in the data set that you have in hand. Now, this is a simple model, but you could have more complex models, but the process remains the same. Okay. So next we go to the analysis of the model, mathematical analysis. So basically what we look at is an asymptotic solutions, and which are equilibrium solutions. Do you all know about equilibrium solutions? All of you? Has anyone not heard of equilibrium solutions? Everyone? Okay. So then basically you find the null lines, you set it equal to 0, right? And you solve for equilibrium points. Do you know how to solve it, or should I continue, or should I spend more time in this? You all know, right? So this is an example of SSIS model. And basically this is used in gonorrhea, it is used in other disease of similar top, where you are in fact, as soon as you recover, you become susceptible again. Gonorrhea is a sexual disease, by the way. So, but there are other diseases also where you recover and you become susceptible immediately. There is no recovery stage here. So this is the model for that. You recover, where is your recovering happening? Yeah, I gamma, and you go to plus I gamma here. And there is people dying also, and getting births also in this model. So how do we find equilibrium solution? You set it equal to 0, and then you find equilibrium solutions, right? You set it equal to 0 and you isolate S and I. So there are two solutions. There are one disease-free solutions, which is I0, S0, and the other one is endemic solution, which looks like this. I is this one. Is that okay? This is making sense or no? Right? So, is this solution always exist? Check the existence, right? Existence is, this has to be, because we are talking about disease, right? Disease cannot be, number of count of cases cannot be negative. So this has to be positive. So beta has to be greater than this thing. Beta has to be greater than this thing in order for this endemic state to exist. Okay, and basically this is an R0. This is one way of computing an R0. This is not the only way, but this. So there are two equilibrium. One when I is 0, and the other one when I is this, and this condition holds. Okay, these two are the equilibrium solutions. One is a disease-free equilibrium solution and one is a endemic equilibrium solution. SIR model the same way. You set it equal to 0 and then you compute it, you get endemic labels like this, and the criteria for existence is this term has to be greater than 1 in order for I to be positive. Right? Now, have you who has calculated R0 before? Reproduction number for a model? You have? How many of you have? Let me see the raise of hands. Reproduction number, how many of you have calculated? Okay, so all of you, I mean, a lot of people have calculated. So basically, the next generation operators is a way of calculating the reproduction number. So what it does is basically separates the system into nuke infections and just the rate of transitions. And then it computes at the disease-free states two matrices, F and V, and therefore, and then R0 is a dominant eigenvalue of F times V inverse, F times V inverse, and dominant eigenvalue of this product to compute an R0. Okay, so let's see how we will compute. So suppose this is a model, S, E, I, and R, and this is the equation of the models look like. Right? Writing down equations is not difficult. It's just knowing the rates and writing down plus minus appropriately in terms of the equations, in terms of the compartment. And then you set it equal, you basically compute F and V inverse. F and V inverse. So what is the new infection here? What is the new infection? Is this one. This is a new infection. And so this is the only new infection. This is an old infection going from one state to another. This is an old infection going from one state to another. But these are not new infections. So only beta SI is a new infection. So it's basically beta term is the new infection. Rest. So why is it 2 by 2, not 4 by 4? You could have 4 by 4, but only taking infected compartment. This is only taking infected. Which are infected compartments? Susceptible? E and I is. So R is not an infected compartment, right? It's a recovered. People have recovered from the infection. They are not infected. So only these two equations are important in the reproduction number. E and I. E is people who are infected, exposed basically, but not infectious, and I is the people who are infectious, right? So you only take E and I equation and you look for terms having new infection, and only this beta SI is a new infection, which is right here, and then rest of the terms are here. Kappa mu is here, and then this kappa is here. And then basically E, because it's an E coefficients on this line, and I coefficient on this line, basically. So there is no I in this equation, and there is no I in this equation because this term is going in this F matrix. Okay, I'll show you another example, but just a quick glance of it. This F and V is easy to find. This is a transition matrix of infection. This is a new infection, basically. So R0 is computed by calculating the product of, you take a V inverse of that. By the way, before that, you are taking partial derivatives with respect to E, D of this equations by E, and at x0 stands for equilibrium, disease-free equilibrium, which is 0, 0. In this case, 0, 0 is a disease-free state. And then basically, then you compute F and V at a disease-free state, and then you compute F times V inverse. You have to take V inverse, you will get F times V inverse as a G matrix, and then you compute the dominant eigenvalue, which is what it is mentioned here. So this is very, very simple to work with. but if you follow these 3 steps, there are these 3 steps. Let me see if I have it somewhere else to compute this thing. Does that make sense? So this is, if this is the system, SIR system, we want to compute an SI reproduction number for that, then we follow the same step. So we rearrange the system so that X is an infected state and Y is an uninfected classes. So first you rearrange it, and then you only take X. This is the X is the infected compartment, and then you calculate F and V from there. So it is computed at disease-free equilibrium usually. Disease-free equilibrium you have to compute from the model, and it will look like third step. So this is 1, 2. Third step is computing F and V matrix, and then therefore basically you will find F and V in the fourth step. F is the partial derivative with respect to the disease state at the disease-free equilibrium. The product is called as the next generation matrix, FV inverse. So let's see what is this thing. So for example, F and V in this case is these are the two. This is the only infected compartment. Only infected compartment. So F consists of new infection, which is this, and rest of the terms goes in the V. Right? And so di by dt is the only infected equation, which is F vector times V vector here. And then F, this is script F and the script V, and this is F, capital F and capital V, which is partial derivative with respect to I at the disease-free state, and the this is also a derivative with respect to I at a disease-free state, and that will give you F and V. And inverse of this is 1 over mu over gamma, so beta times 1 over mu over gamma, which is FV inverse. And that's, in this case, it is 1 by 1. So your R naught is this beta over mu plus gamma. If we, okay, so this is what the calculation look like. If you redo the calculation, now here, this is SEIR model. You have an exposed class, right? And this is an infected class. And so now you will have F as a new infection. Is that the way you have done it, or you have done in a different way? Same way, right? But this is a common way to do the next generation matrix. It has exposed and infected compartments basically, and then you compute F from the script F, and from script V matrix, and then compute the V inverse and the FV inverse product, and that's the eigenvalue, dominant eigenvalue of this is R naught. Okay, for this one, disease-free equilibrium was, for this model, the disease-free equilibrium was this. How do you compute? The way we showed, setting equal to 0 and finding the disease-free equilibrium. This is a model with SIS with 2 strains. There are 2 strains, I1 and I2. Susceptible, I1 and I2, there are 2 strains of the disease. And they are interacting with the 2 strains are infecting. So the susceptible can get infected with the first strain and the second strain. And the different strain have separate equations. So same thing, you calculate script F. So there's 2 infected compartment, I1 and I2. So this is script F and this is script V. New infection in script F and all other transition in the V matrix. And then you compute at disease-free the partial derivative with respect to each of the infected compartment, which is I1 and I2, and that will give you F, and similarly V matrix, and you compute inverse of V, and then you have basically F times V inverse, which is next generation matrix, and there is basically the dominant eigenvalue of this, which will be maximum of these two. Right? These two are the eigenvalue because this is a diagonal matrix. So this is the R0. What it is saying is it depends on which strain is more dominant, and because it's saying maximum of that ratio, and depending on that the disease will propagate or not propagate. So this is for the two strain model. This is a model for computing R0 for TB with the exogenous reinfections, and this is basically people who exposed are also getting infected in this, so I is infecting E. I is infecting E. That means there is a dormant state. TB has a very special type of dynamics. The patients remain dormant. They have infected, but their infection remain dormant. They are not infectious. But once they come in contact with the infectious person, they become infectious. That makes sense? So that's an exogenous reinfection, it is called. Okay, this happens in TB, and therefore, this term is here where I is infecting E. Can you see that? Right? So this is natural term where I is infecting S people, and they are moving from here to here. Right? So this is very common in TB and this type of model. Same way, you have to compute script F, script V, you have to compute disease-free equilibrium, then you find partial derivative, you take V inverse, F V inverse. By the way, how do you find these things? With the hand or with some software? Hand, you can definitely do it, but has anyone used symbolic computing? Do you know what is symbolic computing? MATLAB. So MATLAB has a package called Symboice. What is it? Okay, but so all the this programming language has packages in it that can do symbolic computing. What is symbolic computing?
Instead of real values as variables.
Right. So instead of giving a numerical values, we are using Greek letters, and we are asking it to find inverse. We are finding inverse, we are finding product of the matrices without giving numerical values of these Greek letters, right? So those are symbols you are using to compute the calculation, mathematical calculation. That can be done by the many, Maple does it, Mathematica does it, right? MATLAB does it, Python does it, R also has a packages like that. So we do symbolic computing because it speeds up the process of mathematical calculation. And therefore, and then eigenvalues becomes very difficult once it is maybe 4 by 4 matrix. It is very difficult to compute eigenvalues. In that case, symbolic computing helps a lot. Now, if it is very complicated, the symbolic computing may not work very easily. Anyway, so let's stop here actually in this one, and we will do some simulations actually. So can we share the files in the Dropbox or in the Google folder?
Yes, sir.
Yeah? Okay. So I'll send it to you.